Hello, everyone. We are super happy and lucky to have Professor Mengjia from MIT to serve as our interview today. I'm Jianming Tong, a PhD student from Georgia Tech.
I'm Zishen Wang, a PhD student from Georgia Tech.
I think we can get started on the question. Yeah, could you give us an overview of your journey from when you first got interested into computer architecture research to today?
It will be a long story. So when I was an undergrad, as most undergrad, I just found programming is fun, is interesting, so I decided to do computer science. And there's one lecturer, he's a very good teacher in the sense that I find a lot of lectures, they didn't really stimulate my interest in the specific topic. I kind of got my fun from working on these like labs or PSETs. But for that specific instructor, he taught computer architecture. And the way he taught is that you can feel that he kind of thoroughly consumed all the knowledge, and he tried to talk about this in a very different systematic way, different from what you read from the book, the computer architecture book. So. And the way he described all these trade-offs just got me very interested in it. So that is kind of my very preliminary stage, like very starting point that I got into computer architecture. And then when I joined Joseph's group, my advisor's group, at that time, I barely knew anything. And Joseph said security is an important topic. And I trust him, so I just started working on that. But after working on it for maybe 2 or 3 years, I had a strong feeling that I'm working on, security is indeed an important problem. But as a computer architect, working on security, I feel like I'm a second citizen because software security seems to be more important. Like a lot of work at that time was focusing on how can I design architectural solutions that can improve the performance of some software mitigations. For example, you can imagine if you have some shadow stack, it used to be a software mitigation against like a buffer overflow attack, and people implement in software, but that is too much overhead, so you want to implement in hardware. So this kind of research was the mainstream at that time. So it's still very nice, but I find it's a little bit second citizen because the software people will think, oh, you guys are just doing some performance optimization for us. So I also remember that there's time that my advisor asked me to write a statement for applying for some female workshop, etc. And while I was working on the statement, I just could not convince myself it's really an important problem to work on. But I'm very genuinely interested in security because when an advisor asked me to work on security, I took the security classes at IEEE. So I'm generally interested in security. So I really want to find a problem that can make me believe that it's worth spending my time. So one of my lab mates gave a presentation about there's a paper published around that time called "Get Off My Cloud." So that paper is the very early paper. People did these side channel attacks in the cloud. They did it. It's not like in a controlled environment, and I found it super interesting. And I had a chat with Fangfei Liu. She's now a researcher at Intel Research Lab security team. I met her at ISCA. And we had a long chat because you have these receptions. You took the bus together, so we had a long time to chat. And she encouraged me a lot because she said it's not too difficult to enter this, to do research on side channel because when I got started, I was very confused by all the crypto algorithms because you need to attack these crypto implementations. And I got very confused about this crypto stuff. But she encouraged me that it's not too difficult and encouraged me to just, and I can see that she's very enthusiastic about the research. Then I just, that is time, I think it's almost in my 3rd year as a PhD, then I just started that, and then things just move along in that manner. I would say things became more it became smoother when my first paper got published and I got way more confident. And but my interest about this topic just keep growing. And my advisor is super supportive. Joseph is super supportive, and especially when Chris Fletcher joined UIUC as a junior faculty, I find I was really lucky that almost always at the right time of my life, some good people come up. So Chris, he knew a lot about security. So I would say Joseph gave me a lot of training about how to do research, these very basic and fundamental skills. But our group was not traditionally working on security, as you know. But Chris has a very solid training on security, and his understanding of security is very deep. So I learned a lot from him, and he's also generally very enthusiastic just about research itself. So I also got influence from him. And now when I started the research group, I think I work with my students, so they also give me a lot of energy. Now I think I'm more, as I mentioned in my previous, I mentioned before that I now want to explore more, not just focusing on the computer architecture layer. I found it's more fun to explore the neighboring layers, like how to connect it with system design, how to connect not just kernel, like low-level operating system, and programming languages and formal methods. So like the whole end-to-end process, like you design and you verify, and you also do attacks to discover new vulnerabilities, to discover a blind spot in threat models. So attack, defense, and verification is like a cycle from my perspective.
Got it.
Yeah, that's very inspiring to hear that. I feel be passionate about what we are working on, and talk to people, listen to presentations, and also to read papers, and also to think deeply on that.
I found that it just happened in this manner, and I really appreciate all of them that at the right time of my life, they just give me so much inspiration. It's a chain of effects.
Yeah, yeah. And I think that's like naturally bring up to our next questions, because you did all of this great research and have many accomplishments from the secure computer architecture community. What do you think is the one thing that enables you to do the meaningful and impact work with people from different background, or start this collaboration?
Oh, collaboration-wise, I want to maybe tell the audience. Noah is naturally, I know that when I was a PhD student, I didn't collaborate with anyone, honestly. Only when Chris joined, I would say that in the first 4 years of my PhD, I would not call them code collaboration. It's more about I work on something by myself and I need some help. And I seek help from my lab mates. Joseph has a very good lab culture that they tend to help each other, especially I have some English issues. So they always give me feedback on how to polish my paper writing. So I didn't really have a serious collaboration in the early stage. It's more like I just learn. Like sometimes you paired with a senior student and you learn with them. At that time, I paired with Yasser, another student the same year as me. So we just work with each other, learn from each other in that sense. And only when Chris joined, it's not that I seek collaborations from him, kind of. It's like just the right moment, and we find that our research interests aligned, and the collaboration just automatically start. So sometimes I met some students, they are a little bit bothered by that, oh, I do not have too much collaboration, like I just do solo research. I think I want to say that it's totally fine. And once you find someone whose research interest aligned and also some arrangement or schedule works out, the collaboration will be just happen naturally. And only such collaboration, it will last long, I would say. So even when I started as faculty, I find it's actually in the beginning of my faculty, I'm still trying to figure out what I should do, what is my mentoring style, etc. things. And it may be a little bit distracting to collaborate too many people. Yeah, so I think I want to send an in-time message. I know the community kind of think the more collaboration you have, the better, okay? I would say it depends on which stage you are and which kind of projects you are thinking about, which kind of collaboration you want to have. I would say for junior student, it's more about learning, right? So maybe just find opportunity to learn from another senior student with your advisor. It is maybe already a sufficient setup, so do not need to be overly bothered. Once you are reaching a certain stage, the collaboration just happen automatically. I have, as a faculty, I mainly have like collaborations with Joe Emmer when I joined because even during the interview season we chatted a lot. And now I had this collaboration with Thomas Busha from EPFL. He used to be a student at MIT, and Sharad Malik from Princeton. I find my collaboration is more like, I like this collaboration where we are complementary to each other, and I find that every time I talk to them, I learn so much. So I hope they also feel like they learn something from me. But I find this kind of collaboration is very fruitful. So I think for example, Sharad, indeed he's such an expert on set solver and he knows all the things internally, but I view set solver as something black box. And when I talk to him, I can feel like he think about problem differently from me. You can feel that, okay? You can feel like sometimes it ends up with like misunderstanding about each other's terminology, but as the more you talk, you feel like, okay, this person, he think about things from a very different perspective. And then I just find it very interesting. I want to figure out how his view looks like. So I also go and check his slides for the hardware security plus verification course he offered at Princeton, and I check his slides, and he's a very nice person. He also offered to like even go through the slides with me so that I can get myself understood. It's fun. Like every time we meet, I find that I learn something new. That's the collaboration I think I will have, like I plan for multiple years, like very long-term collaboration.
That's super interesting to hear. Yeah.
Thanks so much for that insights on the collaboration side. We do learn a lot as a young graduate student. They also come to the next question because this is related to the research.
Okay.
So I love a favorite metaphor. So attacking Harvard is like robbing a bank. People find a way in and get the money out. So Matcha finds all the way into the Harvard early and then tells the vendors how to secure it to avoid money loss. The entire research topic is so critical and intriguing. Could you give us an overview of your journey when you started this thing?
Oh, when I start this attack stuff. So as you know, at that time, I think there are not too many people doing offensive security research or attacks in the computer architecture community. And I think even when we submit papers to the computer architecture community, we were rejected. People think like attack is a bit evil. I need to really thank a person. He may not know he actually influenced me so much. He's Michael Bailey from UIUC, and now he's a faculty at Georgia Tech. Actually, he's the head of the security college of I think that one. He used to be at UIUC, and he was teaching this very good security class at UIUC. That is an undergrad security class, and basically you all the lab assignments are hack. You are developing attack, and you can see that when the instructor he described these attacks in theory in class. It sounds very intuitive, very straightforward. But actually, if you are trying to implement it on a real system, the biggest thing is that you are doing it in real. It's not like a simulated software system. It's like really a virtual machineware. So you need to figure out all the details, and it's very similar to like you are playing jigsaw puzzle. Like you need to make pieces align together to eventually make it. So you feel really accomplished after you get it done. I remember I took the class maybe even in my first or second year as a PhD student, and I was so obsessed with the course, so I finished all the lab assignments always ahead of time, always, because it's just a lot of fun. So that also drove me to develop my own hardware security class at MIT that we truly believe. I did this with my student Joseph Ravihandra and a couple of other students. Many of my students contribute to this course because we all find it's very enjoyable to make these things, make what we think fun, expose it to others, let others also see how fun it is. So we really believe you learn by playing and working on things rather than just listening to these lectures. So we spent a lot of effort to develop these lab assignments, and we say no simulator. We want it to be done on real hardware. Mainly because for software classes, they can attack the software system. You can set up a virtual machine, etc. But for hardware, attack is very hardware specific. So we actually put a lot of effort to actually make these attacks work and make it even tractable for senior undergrad or junior PhD students or masters to work on it. And we got a lot of good feedback. I don't think all of the students will work on research related to hardware security, but I find it's a very good way to learn system. If you think offensively about system, for example, if you want to really make the cache side channel work, you will know cache in depth, okay? So it's another way to learn system, I would say. And people get a very thorough understanding about how cache works.
Really appreciate that. And then I think as a student here, they are super lucky to get this practical attacking on the hardware stuff.
Yeah, I feel that also equal a lot from our as a peer student, our research experience. So the stuff we can learn a lot of stuff is when we make our hand to really build something, can learn a lot of stuff.
Yes.
Yeah.
I like that approach. Yeah.
Okay. Yeah, and let's come to research a little bit. So how do you define a good problem? And say if you're a graduate student this year, what problem you will work on?
It's a difficult question. I mean, I would say if a student work on security, let's say, not a broad topic. There are many, I would say, the beauty of this is that this community has so many different people. And we all think about research in different ways. So I would just say what my way is. I think when I work on a problem first, it need to have the right motivation. Like it is a problem that is unsolved in the sense that I need to convince myself it's not really, it needs to logically make sense. For example, let me give an example. When I work on cache side channel attacks, I talk to my advisor because, I want to just say I want to work on this. But it actually is not easy to convince my advisor to work on this because it is such something, imagine that your second year PhD student came to you and say, I want to work on a random thing. You will not really feel like it makes sense, right? So Joseph told me that, is this a real threat in the sense that the cache has so much noise, there's so many things going on every nanoseconds, right? Finding a signal in the cache is almost like find a needle in the ocean.
Yes.
And is this really something makes sense? It is very valid concern. It's a very valid concern, I would say. So if I want to commit it, I have to make sure I convince myself it's something realistic. Otherwise, why work on a defense mechanism, right? So the first thing I did is I replicate the tag in the paper. And I remember that I showed Joseph that I indeed run these two threads and that they can observe each other in a real machine. It's not too difficult if you do a covert channel at that time. But of course, if you never do it, you never get experience. So by doing that, I kind of roughly convinced him it's a signal is there. I can clearly detect it. So this can give an example that at least I need to confirm it is the problem, it's a realistic problem we should work on. And then the second factor, I would say, maybe during my PhD, I'm still in my survival mode. I need to be very honest. Like, I know PhD is tough, okay? I think the ending of my PhD is great, but the whole process is still very struggling. It's more like I feel like most time I'm in the survivor mode. I want to work on something, get something shipped, okay? But at least I confirm it's a work problem. I find that if I convince my advisor, usually it makes sense. And then now as a faculty, I think my philosophy slightly changed. I want to make sure it is something I want to work on something I learn new things. I do not want to repeat the same thing as before because otherwise I don't think my time and my life is well spent. So therefore, after I got started, I kind of started this new direction using formal methods to verify the security design, and also using information theory to quantify leakage. So this is kind of a two new branches I started after as a faculty. I still continue some of the work as a PhD student, but and the third direction is more like how do you leverage programming language to ensure your software hardware co-design is secure. So let me explain why I started that. So the time when I graduate, I was very happy with all these security problems got big attention, right? Then there's so many defenses got proposed. And as I'm sitting on this PC review as a reviewer, I find for many of the defense papers, they propose a defense and they need to argue their defense is secure. So they will write a very long security discussion section to discuss why my defense is secure. It's a mental exercise. As a reviewer, you need to read the section very carefully and think what has not been considered by the authors. So when I review these papers, it's indeed a cat and mouse game. Like, I need to see whether I can spot some bug in their design. And sometimes you find some bug and you write in your review, oh, this case seemed to not be addressed. Then the authors came back, say, oh, we can do this patch to address this. So that is kind of what you observe in the PC review. The same thing happened in industry where Intel patched something and attacker find another way to go through. So it's really keep repeating. I think repeating is, this cycle as evolves, is definitely your system also become more secure. But if you repeat it enough times, I find I cannot be satisfied enough. I feel like, are we really making progress or not? So I was trying to see whether we can. I kind of feel like maybe it is not really proposing a new defense mechanism. Maybe not really the bottleneck of the community. Actually, to reason about the security, how to reason about security seems to be very underexplored, in the sense that when we design some obfuscation mechanism like randomized cache, it's very difficult to reason whether it's secure or not. That's why we did like CASA and media to see whether we can develop quantitative approaches, like using mathematical models to quantify the leakage. And then for a lot of speculative execution attacks, you need to delay it, you need to do this and that. You describe all the different ways and the scheme becomes more and more complicated. Then eventually find we need to seek help from formal verification. Then when I talk to these formal verification people, I find, oh, it's such an alien domain to computer architects because they speak completely different language. And so I'll even attend, even as a faculty, I like attend classes. I almost try to attend a lecture by some of my colleagues every year, like maybe once per year. So I attended Adam Chipala, my office neighbor's like formal verification class, like it's about CoG. CoG is a manual prover assistant. And my conclusion is that it's too difficult, and these people think in math, and it's a completely different way from computer architects. So even if they can do some verification, they just cannot solve our problem, in the sense that given the big gap, every time I have a new design, they don't really understand what kind of trade-off we are making here. And when they verify it, they need some architectural insights to address their scalability issues. But we do not talk in a smooth manner. And for us, we're just unable to use this very complex tool, which requires so much manual effort. So I feel like the really challenge here is how can we design these tools that can be usable by computer architects to verify their design. So and that leads to my collaboration with Thomas and Sherrod, and that's why you see they are from Thomas is from the PL community and Sherrod is from the EDA community and formal methods community. So that's why I find that we learn so much, and they are also very passionate about this direction we are taking. That to how can we leverage architectural insights to make verification actually accessible and usable, and it's more like you learn something new and you also combine what you know before. Another thing we are also working on is I believe that because different applications have different security requirements, so eventually we want our defense to be software hardware co-design, that you do not deploy a universal defense mechanism against all the applications in the world, because some applications even do not care about security. So this also leads me to do this, like how can we use some programming language technique? And that is also something I learned through my students, kind of. So I would say if some students, they start work on security this year, what they should work on, I think from my perspective, they can work on attacks, because I feel like as a starting point, if this attacker mindset can help you to think out of box, so that you can see things broadly, like you think about, you rather following how the hardware was designed to be useful, you think about what it's not designed useful. So it's like training your mindset in this manner, okay? And if the student is also interested in programming language, I would say it is a very big underexplored direction, because PL formal methods and security and architecture, when you mix them together, there's many interesting problems, and they are very challenging. I feel like they're still in the very initial stage, so there's a lot of things can be done.
Yeah, seems like there's so many interesting things for us to work on in this domain, and I hope it's inspirational both for us, but also for the students and in the watching this video.
Yep. And also for being this age at this particular year, I think it's really appreciated for killing the game of chess like catch and mouse problem, and then there is a quantified opportunity to end the entire thing to understand where we are. So following by that, there is an immediate question: what is Mengjia looking forward to the most in the Harvard attack and the mitigation in the next 10 years?
I think usually when we study the problem, we try to make sure it is very generalized, and the security problem target all the cases, like side channels, it works in the cloud setup and also in the personal laptop setup. I will be very curious because, as you can sense that I want to try something new. I do hope that, because side channel for now, we have a roughly good understanding. Honestly, it is very difficult if someone come up with a side channel attack that can significantly impress me. If it happened tomorrow, great. I'll be happy to read the paper. But in the last few years, there will be still like news report, something put on the spotlight, and you can see there's some very, very cute attacks. I would like this attack, but I don't feel like they surprised me feel in that manner. So I do hope that if there's any new problems people can discover other than speculative execution attacks and side channels, it's not there yet, I would say. That will be something I'm looking forward to, because once you work on the problem, I like the problem I'm working on, because I don't think it's solved. It's far from being solved, and there's so many interesting things we can think about. But I would say if I want claim the biggest thing, it will be something like spectrum meltdown. The first time this very long-lasting performance optimization feature, spec execution, can be used for attack, is the moment that you find yourself very shocked, right? And that is opened all these new directions and got so many people interested in this problem. So I would say if you ask me what will impress me in next 10 years, it need to be something new, like new threats. I believe there will be, because security is always like evolving, because you can never avoid security problems, new devices, new setups, new technology. Every time you have these things, it improve, make people's life more convenient, okay? And then it will just create new security problems. So I'm looking for this unknown class or category of security problems other than side channels to pop up.
Also on that, I do have a question as well. So I think like side channel is usually within a single identity. Is there any potential unknown space for clusters, even for distributed clusters?
So network side channel is also something people have studied before. Like even before spectrum meltdown came out, network side channel, like if you are communicating with each other on the internet, the size of the packet, you may encrypt the whole packet, but the size of packet or the communication pattern of the packet can also reveal some information. So this has been known before. And I think not in the computer architecture domain, but in applied crypto domain, they are looking towards solutions to address this issue. Because for them, the attack doesn't require a lot of very detailed system tuning, like hardware tuning. They just need to capture, because you can pick up the packet, the encrypted packet in the network, and you are trying to use all sorts of complicated analysis techniques to figure out what is going on. So in applied crypto, they are looking to these problems.
Yeah, I really appreciate that insights. Also, security also comes with overhead. What would you think the cost of the hardware security gonna be in future? And also, is there automated way to auto-discover the potential vulnerabilities and then defense it?
I would say cost indeed is a big issue. To be honest, I haven't been in industry for a while. From my perspective, other than cost, maybe the more important thing is hardware complexity. Another important factor is hardware complexity. So some numbers I've heard is that for Linux, if you want to protect your kernel, if you enable that software mitigation, it's already give you like maybe 1.5 kind of performance slowdown, and the people can, it's okay with that. It's really the trade-off between how risky it is and how much you want to pay. But hardware complexity is a very tricky thing in the sense that now I truly believe the more complex your defense mechanism is, the more difficult to ensure it is bug-free. So sometimes you put something complex into the hardware and introduce even more problems. So how can you ensure how can you reason about the security or cleanness or correctness of this mitigation mechanism becomes super important. And it's better to make the mitigation simpler. But the problem is that the existing hardware itself is already very complicated. That's why I kind of so passionate about this verification direction, because I find that may be the bottleneck.
Got it. Do you think there is an automated way to auto-discover these bugs within this super complex hardware, and then is there a way to automatically secure it? Or is it going to be something worthwhile for looking in the future?
Given the current power of large language model, nothing is impossible. But when you say automated, there are many different fashions of automation. I would say formal verification itself is also one type of automation in the sense that, for example, the technique we use is like model checker. If you set up the problem in certain ways, the model checker do things automatically for you because model checking is a very low barrier technique. People even call it push button technique in the verification community. But you need to set up the problem properly, like set up the property exaggerate checks properly. It's like in large language model, you need to do the prompt properly. But I would say there's still a gap between prompting versus you rigorously configure your problem property to be checked by the model checker. There's still a big gap, okay? What I meant is that there's a big chunk of automation you do, because for formal verification, you are not only trying to derive the unbounded proof for the design. Usually, if there's a bug, the model checker can also automatically find the bug for you. So it's already a type of automation in that sense. But the manual effort is that you need to understand the problem in the correct fashion so you can formulate and configure the assertion in the proper way so that the model checker can check for arbitrary input. I find the vulnerable configuration, I find the input sequence to trigger the bug or trigger the leakage. Okay, so it's already an automatic search problem. It may be different from the automation from what you have seen in large language model or machine learning technique, because this one is an exhaustive search using math and set solver as the back end. But the other one, I think it has some magic in it. It's promising, I would say. It's definitely some direction people should explore in using large language model, using like machine learning techniques to automate something like that. Attacks, maybe. Yeah, I see some research coming. Some people are start working on this direction, and I think it's very promising. It's just so far we haven't seen great breakthrough you will always see that, whether this machine learning based technique better than human being in terms of doing microarchitecture attacks, right? It's not easy because, for example, I think a lot of software classes, they are very concerned that, okay, the students can use ChatGPT to cheat on the lab assignments. So far, we do not have such serious issues with our hardware security class because our attack code doesn't really have these semantics, right? So it is really how you interact with the underlying hardware, and so far, not yet, okay? But I'm not surprised if in the future ChatGPT can do that. But for now, not yet. ChatGPT is unable to really produce very high quality, these detailed cache attacks work perfectly on our machine, in the sense that they are still limited in that sense. But I will not be surprised if one day they can do that.
Really appreciate the insight on this. And also, there is one last question regarding the automated way. How do you think this part of vulnerability is coming from insufficient coverage on their test within the industry, or how much is coming from other reasons?
So in my class, I told students that usually the bug or security vulnerability arises for multiple different reasons. Okay, so you may think that usually when we see a bug is that you have a specification of the system. You describe how the system should work in this way, and then the implementation doesn't match your specification. That is usually we consider as a bug. But what I can see in industry is that their specification is insecure. In the sense, they say, I want to design the system in this way. Their RTL matches their design, but the original idea, but the original idea has vulnerability. Okay, that's usually the case I see. That's why in our verification line of work, we 2 years ago, I think 2022 or 2023, ISCA, we published this pensive paper, which is trying to do early stage microarchitecture modeling for security, because we do all the early stage microarchitecture modeling for performance estimation, like Gen 5, right? But in this early stage, you are thinking about how the process should look like, should work. But most of these are for performance estimation, not for security. They are missing a lot of important critical details that make the model unable to be verified using formal methods. So for that specific work, we are trying to say, okay, maybe even your idea, the microarchitecture idea is insecure. Okay, so that is one level. And then once we verify your idea, like the high-level microarchitecture idea is secure, then we want to check your RTL implementation is secure. So back to our question, industry, why they make all this mistake? I think usually there are two categories. First is that in their specification, some of these things are underspecified. For example, like in your processor, you're designing a x86 processor. The only requirement is that this x86 processor should implement my ISA correctly, like the adder should work correctly in this way. It talks nothing about speculation, right? The ISA doesn't talk about speculation. So it is under specification in the sense that it's a free variable. No matter what you do with speculation, your processor is correct. So they didn't include that in their specification. Then in this case, of course, so that is really, most of the time is that I think as time goes by, things will shift across these two categories. But I would say in the early stage, we are still in a category where that the security feature is underspecified. It's not specified there. And so there's no coverage issue yet because it even was not mentioned. And then I think as time goes by, later we will see now we are more security aware. Then in your implementation, then you need to be very careful. Okay, I want to have this security feature, whether I actually properly implement it, and then I test it, and the coverage will enter the view.
Learn a lot. I feel this kind of research will definitely helpful for the future industry.
Yeah, we talk like a lot of interesting aspects of the security. Probably we can also briefly touch upon the reliability, because we know you also did a lot of fantastic work on the reliabilities. For example, the silent data corruptions. So how do you think the challenge of this SD system, especially in the area of generative AI, these large-scale data centers?
Yeah, it's very challenging, and I have to say that this direction, like the reliability project, is completely led, independently led by my student Peter Deutsch and Vincent. He's a visiting student in my group and who will also join as a postdoc soon. So all these challenges I see is more like I see from their discussions. I think the tricky thing here is these reliability issues, they occur so infrequently, but they're also frequent enough to be bothered when you are in these large-scale data centers. But actually, when you try to observe it on a single machine, it's very difficult to observe. So you have to assume some fault model. There is some well-established fault model, but maybe this fault model cannot fully explain what's happening now. So people need to find the actually root cause, which is still mysterious. Once this root cause is unknown, then you can only assume something as a computer. And usually this root cause happen in the physical layer, the circuit layer. And as computer architects, if you want to work on the computer architecture layer of the problem, you kind of need to assume something, which is a little bit uneasy for me to do in the sense. We have to talk to a lot of experts in that in fault models. With machine learning technique, I think it's even more challenging in the sense that the very very seminal work by Joel Emmer, which won the Test of Time Award 2 years ago, I think maybe 2 years ago micro, or maybe 3 years ago micro. It's AVF, like architectural vulnerability factor. That is a seminal work about measuring, quantify reliability issues in the processor. Basically, it tries to distinguish between whether a fault in your circuit or in your RTL can actually trigger a program visible error, okay? And they are trying to distinguish between these two cases because some of this error may be masked out. Like if you put something in a register, temporal storage, and you never use it, this will not manifest as a real bug, right? So they are trying to distinguish that in the whole process. For example, if you have a bit flip in a transient instruction which will be squashed later, this will not affect the final result, or if you have a bit flip in the branch predictor. So that is very insightful and kind of helps community to make a lot of progress in reasoning about reliability. But now, if you are talking about AI and machine learning accelerators, in addition to this RTL level or hard computer architecture level of reasoning, even if you have a program visible bit flip in your machine learning parameters, let's say a model parameter, a weight, it is not easy to claim whether this bit flip will actually result in the model behave incorrectly. So it's another layer of the tunnel, very murky tunnel you need to go through to reason about the impact of a fault. So that is very challenging, I would say. And usually this fault injection simulation took a very long time. If you do it for large models, then it's almost infeasible to be done in a very authentic way. So that is so far is the challenge I see. And for this kind of things also, it's very industry dependent. It will be better if the industry could release more information or let the academia use their faulty machines so we can have better calibration about what is happening. But establish this kind of connection it requires mutual effort and it's not that easy.
Thank you so much, Professor Yan, for sending us here today to have this interview discussions. And I hope this interview is helpful for both for students and also the computer architecture around the world.
Thanks a lot. These are all very good questions. Thanks for chatting with me.